So first of all, before we do this section, I want to remind you of the last section. So last time, we talked about proportions. And sampling distributions for p hat. This was the last set of notes we did. And we said that the mean of p hat was just p. And then the standard deviation was the square root of p times 1 minus p over n, or pq over n. Right, that was those were our formulas for the sampling distributions for proportions. So keep that in mind as we move forward here, because we're about to talk about distributions for means. So when we come across a question, one of the first things that we need to establish when we start to look at, say, a chapter review is going to be, is this a question talking about means, or are we talking about proportions or percentages? So make sure we keep that in mind as we move forward on these problems, because if we're talking about proportions, we've got a different set of formulas for that we've already talked about. All right. Now let's look at these notes. Proportions arise most often when we are interested in categorical variables. So we're interested in like what percentage are involved in A versus B versus C, or what percentage said yes or no to a question. But most of the time when we talk about quantitative variables, we're talking about like median or mean. And so we're going to talk about the same idea is going to happen for these large sample sizes. As long as we're sampling a large enough group, then we're basically going to be able to treat this sampling distribution, right? Any possible sample I could take of that size, we're basically going to be able to treat it like a normal distribution. And you'll notice again, larger samples are going to give smaller amounts of spread. So that's what's going to happen as we move forward here. This time, very creative. All right, this time we're talking about means. And the mean of x bar, you'll never guess, it should match the mean of the population. It should be centered at where the center is at, just like the proportion one should be centered at wherever the proportion actually is. Standard deviation for x bar is going to be the standard deviation of the population over the square root of n. Notice again in this formula that if we make n bigger than standard deviation, the spread, gets smaller. N goes up means the denominator goes up means the number gets smaller. So the larger the sample size, the smaller the standard deviation of that sampling distribution. So that's what the mean will look like, and that's what the standard deviation will look like. So again, which formulas you're going to use are going to depend on, is it a question talking about means or is it a question talking about proportions? But then after that, the process of what we're going to do in this section is going to be really similar to what we talked about in the last section. Because we're going to treat it like a normal distribution. We're going to figure out the mean and standard deviation with these formulas, and we're going to do some normal CDF work. So a lot of these problems are going to, the process of them is going to look very similar to things that we've already done. As long as the population is at least 10 times the sample size, and we talked about that at the Zoom meeting on Friday. And this happens regardless of the shape of the population distribution. The sampling distribution will always have this mean and standard deviation no matter what. So there's your standard deviation, sigma over square root of n, etc. All right. We basically already talked about this slide. It's mostly the same. All right. This one is important because we're going to make an important distinction between these two questions. So on this example, you're being asked two different questions. And we want to make sure that we make a distinction between the two. So we have the mean and standard deviation in front of us. And it says find the probability that a randomly selected young woman is taller than 66.5 inches. And then it says find the probability that if I select 10 of these women, that sample will have a mean that is more than 66.5. So before we go and solve this problem, the question I want you to think about, I'll give you a few seconds to consider it, is which of these is going to be more likely to happen? Picking a single person that is 66.5 or taller, or picking a sample of 10 that has a mean that is 66.5 or taller? Think about it kind of conceptually. And in terms of picking samples and picking means. And we'll also show it with the calculations that we do and the formulas that we work out. So here's what to think about. Which one do we think is more likely, the first one or the second one? First one we're saying is more likely? How come? Let me steer you in the direction. What's the difference between what needs to happen in order for a single person versus describe to me what needs to happen in order for a sample of 10 to have a mean? that's a stronger statement. And the reason is, if we're picking a sample of 10 and we have a mean above 66.5, then that's saying something more specific. That means that we're picking multiple different people that have the mean that high, that have values that high. In order to push the mean above it, then there have to be multiple different people that have that high a value. And so it is, and since that high a value is farther away from the mean, we're less likely to get a bunch of people that are that high, or maybe a single outlier that's really tall that is pushing the mean that high. Those are both way less likely to happen than a single person. Now, here's the difference between actually calculating these two questions. So in other words, A's probability should be bigger than B's probability. We know that. We just thought about why that was, so we need to keep that in mind when we're going through this problem. If we're just talking about a randomly selected person, then here's the distribution of picking a single person. The height of young women follows a normal distribution. So that means here's our mean, here's our standard deviation, and we can jump right to z-scores and normal CDF. And we have the mean and standard deviation in front of us. So let's do that. Normal with a mean of 64.5 and a standard deviation 2.5. Here's your z-score. If you want to do it with z-scores. Is this going to be my lower or my upper? That's 66.5. If we want the person to be taller than that, lower. Because if I want it to be bigger, then I'm saying that the 66.5 is the smallest height, or the shortest height that I can have. And then I want everything to the right of that. That's where drawing a picture will help. Right? You'll see that that's the lower, that's the farthest left value, and then everything, we're shading everything to the right. So go ahead and actually do that calculation and get your normal CDF, and make sure you get something around 0.2119. Make sure we're all on that page before we go on. So remember, this answer to this next question should be less than 0.2119. And the next thing I want you to do is the next answer that I'm looking for is, in the next problem, what is the mean, what is the standard deviation? Because this answer, remember, is not going to be the same, so we must be based on a different set of calculations. By the way, notice we're talking about means. We're using mu to Denote that mean, not a proportion. So we're using these ideas of mean. And since we are taking a sample, then we need to start using these formulas. So mean is still at the mean. It's still the 66.5. So what will our, one second here, what will our standard deviation be on this one? We take our standard deviation and we divide it by what? It's going to be square root of our sample size, which is 10. And so our new distribution is still going to have a mean of 64.5, but the standard deviation will be the 2.5 population standard deviation over the square root of n. So instead of using these in our mean and standard deviation formula, we're using these two values, the 64.5 and the 0.79. So go ahead and get those calculations and proportions out. Remember, this answer should be lower and smaller than the probability we got in part A. Here comes the answer. Maybe. Eventually. It's common. Hey, there it is. .0057. If you did the z-score formula, the z-score was 2.53, using that mean and standard deviation. On normal CDF, if you're not using the z-score, then you want to put that mean and standard deviation in. If you're having trouble wrapping your mind around these two different problems, I could have asked you this question back in chapter 2. I could not have asked you this question in chapter 2 because it needed these formulas. If you wanted to think about it, this one, in terms of these formulas that we've just given you, then the mean would still be the mean. And then the standard deviation would be 2.5 over the square root of my sample size. How many people am I sampling here? 1. I'm taking a randomly selected person, and so one single person. Well, 2.5 over the square root of 1. Square root of 1 is 1, and 2.5 divided by 1 is still 2.5. So that's another way you can show that the mean and standard deviation will just be this mean and standard deviation that are listed there. So if it helps to think about this as using a sample of size 1, then that might be helpful to you. Questions on any of that?
So how would you take the z-score and get the 0.0057?
Like the 2.53?
Yeah.
So you have your normal CDF.
Oh, you plug that into that.
So the 2.53 is going to be your lower. We talked about why that's the lower. And then mean is, for any time you're using a z-score, instead of the actual distribution, anytime you have a z-score, mean 0, standard deviation of 1.
But you don't have to use the z-score,
Right, if you want to use this, and this, that'll work too. You may need to show some more work. We'll talk about that when we get closer to the AP test on exactly what you need to show. Or actually, we'll talk about that on Wednesday, because we'll look at some actual practice questions. And I can give you more details on whether that works efficiently. Other questions?
Will we ever be dealing with negative z-scores?
Can someone else answer that question? What would a negative z-score tell me? What does a z-score tell me, first of all?
like, don't you know you're wrong? Because that would mean that you're
So what is the formula for z-score? Let's deal with that. So the question was, if we didn't hear it over the stream, the question was asking about negative z-scores, and is that possible? What's the z-score formula? Take the value and subtract what? The mean over standard deviation. Oh man, that's terrible. Okay. S sub x. Let's use S sub x if we're using x bar. X sub x goes with x bar, and same one goes with mean. All right, there we go. So, standard deviation. Standard deviation is always going to be positive. Now, the top, since we're doing a subtraction problem, then a subtraction problem can give me a negative answer, right? And so if the subtraction problem gives me a negative answer, then that means that which number ended up being bigger? X or x bar? X bar ended up outweighing x. Can we have a value that is below x bar? Yeah. So there we can have a negative z-score. So negative z-scores will mean that the value is judging, this is how far the value is below the mean. This value, the 66.5, was above the mean of 64.5. So since it was above the mean, it got a positive z-score. But we could definitely have negative z-scores. What's called the standard normal distribution has a mean of 0, standard deviation of 1. And so if I draw that out, mean is at 0. So I usually go 2 standard deviations above and 2 standard deviations below. Guess where it goes? Negative 1, negative 2 to the left. Questions on that? Or any other questions on this problem? That's a good question. Good refresher on normal distribution stuff. Now, if you're getting a negative probability, then something's wrong. Right? Probability should be between 0 and 1. What's next here? Oh, it is very unlikely. Less than 1% chance. Again, more unlikely than just picking one person. What's next? Here's the two distributions right next to each other. Same mean, but since it's a larger sample size, has a smaller spread, and here's the likelihood. So here's kind of the two pictures layered on top of each other. All right, what's next? Oh, it's a homework assignment. What a pleasant surprise.
How many homework assignments do you have?
I think it's 4 now. I think. I'll double check that. They should all be posted on Canvas. This one will be posted in just a minute.